So let's get back to it. It's been 12 days. Hopefully you haven't forgotten everything. I will remind you where we were. We were talking about Jacobi fields. I'll remind you what the definition is in a second. We're going to continue talking about Jacobi fields for the first half an hour today. And then originally my plan was to move on to chapter 6 about isometric immersions. But that's sort of much more standard Riemannian geometry that you often see in introductory courses, and it's really easy to follow. And I don't need it again in the book until half of chapter 10. So what I'm going to do is skip chapter 6 and move on to chapter 7 on completeness, Hopf-Rhino theorem, Cartan-Hadamard theorem. And then depending on how far we get, if we get to the second half of chapter 10, I might decide to go back to chapter 6, or we might do other interesting things and not talk about isometric immersions. So that's the plan. I'm also about halfway through grading assignment 1. You'll get it back before you hand in assignment 2. You'll probably get it back by Friday. I think assignment 2 is due a week from tomorrow, if I'm correct, something like that. And you can do most of it already, and you'll be able to do the rest of it after I finish the Jacobi field stuff. So recall, this is how we define Jacobi field. If we have a geodesic on M, we always have a fixed Riemannian metric on our manifold. We have a geodesic, then a Jacobi field along this geodesic, so this is fixed data, is a vector field along this geodesic such that it satisfies this equation, this Jacobi equation. This is the second covariant derivative along gamma. So that's the Jacobi equation, and we saw that this is a second order linear ODE. So for a second order linear ODE, as long as you prescribe the initial value and the initial derivative, there exists a unique solution. So this is this space of solutions is parameterized by j of 0 and j prime of 0. So if you specify j at time 0 and the first covariant derivative along the curve of j at time 0, then there's a unique solution. And this is a vector space, right? Because it's a linear equation, any linear combination of solutions is a solution. And we saw that there exists sort of two simple ones. The tangential solutions are j equals gamma prime. This is always a Jacobi field. And j is t gamma prime. This is also a Jacobi field. And then so these are somehow less interesting. So the solutions such that j is orthogonal to gamma prime for all t are called normal Jacobi fields. Normal Jacobi fields. And these are the ones we're really interested in. And this is a 2n minus 2 dimensional space. And this corresponds to taking j of 0 and j prime of 0 orthogonal to gamma prime of 0. Okay. In fact, I'll review some of this near the end of this section. But what we did before the break was to understand that Jacobi fields tell you something, because you see the curvature shows up in the equation. They tell you they're used to understand how curvature affects the spreading of geodesics. Right. So we saw that in some sense, which we made precise before the break, but I'm not going to repeat it, that if the curvature was positive at a point, the sectional curvature, then geodesics that are initially tangent to that two plane tend to not spread out as much as they do in flat space. And if the sectional curvature is negative on some two plane, then geodesics that are initially tangent to that two plane tend to spread out more than they do in flat space. Okay, but the next thing we're going to do is to see another interpretation of Jacobi fields. Another thing they're good for, and that is to identify where the exponential map becomes singular. Okay, so the next is the relationship between Jacobi fields and singularities of the exponential map. Okay, so recall that xp is defined on some open set in TPM, which is star-shaped with respect to the origin, star-shaped with respect to the origin. and it maps into M, and it's smooth. Okay, and therefore the push forward, if V is a point in capital V, then the push forward at V will go from TV of TPM, which is canonically TPM, to TXP of V of M. And this is linear. Okay, and we know that when V is 0, this is the identity map. When V equals 0, XP star at 0 is the identity on TPM, because if I apply XP to 0, I get P. So for V close to 0, XP star V is an isomorphism. Okay, because everything is smooth. So this Jacobian matrix, if you write it in coordinates, the entries are the first partial derivatives, and they're continuous, right? So if the determinant is 1 at P, then at 0, then at close to 0, the determinant will be close to 1, so it'll be non-zero, so it'll be invertible. But even though this guy is defined on all of V, we don't know that this guy is invertible everywhere on capital V. So there can exist V in V where XP star of V fails to be invertible, to be an isomorphism. And because this is going from n dimensions to n dimensions, that's exactly saying there's something non-trivial in the kernel, i.e., when the kernel is non-trivial. Okay, such a V is called the critical point of XP. So it has to be in the domain of XP, obviously, but it's a point where the push forward has a kernel, has a non-trivial kernel. Okay,
Spiro,
so now with that, yeah, yes.
I have a question. It's just about the definition of the domain of XP.
Yes.
So
Yeah.
this is, if I recall correctly, we defined the domain of the just general exponential as
Yeah.
some huge open set in TM, and then we intersected with TPM.
That's right.
So these are just, if I recall correctly, these are just all the vectors whose geodesic with initial point P and velocity V can flow for time 1, right?
Yeah, that's right.
Okay, yeah, just making sure because we've done a
Yeah. So the question was, what is this domain? This is the domain of the exponential map intersect TPM. Okay, so it's all those vectors such that if you look at the geodesic with initial point P and initial vector V, it's defined at least for time 1. Okay, so now I can state the next result, which will follow immediately from the definitions, essentially. Oh, I need a definition first. So, definition, let gamma be a geodesic. Strictly speaking, this is a geodesic segment because I've restricted the domain to some closed bounded interval. And for T naught, something which is bigger than 0, but less than or equal to A, the point gamma of T naught in M is called a conjugate point to gamma of 0 along gamma, if and only if there exists a non-zero Jacobi field along gamma with j of 0 equals 0 and j of t naught equals 0. Okay, so to be a conjugate point, you can't just say, is this point a conjugate point? You have to fix a geodesic, and then with respect to that geodesic, a point on the image of the geodesic will be conjugate to the initial point of the geodesic, if and only if there's a non-zero Jacobi field which vanishes at these two times, time 0 and time t naught. And the maximum number of linearly independent of such linearly independent Jacobi fields is called the multiplicity of the conjugate point. Multiplicity of the conjugate point. It's easy to see because the Jacobi equation is linear, that if I have two Jacobi fields which vanish at time 0 and time t naught, then their linear combination, any linear combination of them will be a Jacobi field which vanishes at 0 and t naught. Right? So that's a linear subspace of the space of Jacobi fields. So that's the definition. We're going to see in a minute what this has to do with the discussion over there. But let me make two remarks and give an example of conjugate points before we come to this result. So remarks, if gamma of t naught is conjugate to gamma of 0 along gamma, I'm not going to keep writing that, there's only one geodesic in the problem, then gamma of 0 is conjugate to gamma of t naught along gamma inverse restricted to 0 t naught. Okay, and this goes from 0 t naught to m. So the picture, if this is gamma, here's gamma of 0, there's gamma of a. So if I have some time t naught, which is bigger than 0 but less than or equal to a, where gamma of t naught is a conjugate point, that means there exists a Jacobi field which vanishes at 0 and at gamma of t naught, at gamma of 0 and gamma of t naught, and we don't know what it does after that. We don't care what it does after that. And you can see that if I look at J inverse of t, which is J of a minus t, this is a Jacobi field along gamma inverse of t, which is gamma of a minus t on 0a. You can just check that, and that's because of the linearity of the Jacobi equation and the chain rule. And therefore, and this guy, J inverse, if you restrict it now, if you restrict this curve to just going from here to here, then this gives you a Jacobi field which vanishes at this initial point of gamma inverse. What have I done here? If I put gamma inverse at 0, this is wrong, right? This is t naught. What am I doing? I didn't want to write this down at all. So gamma inverse at t naught is, this is wrong. You can figure out what it has to be. I'll mess it up if I try to solve it now. So given if you have a geodesic and you have a point which is conjugate to the initial point of the geodesic, you can follow that geodesic in the opposite direction. And so the initial point of your original geodesic is now conjugate to the final point along the opposite geodesic. That was one remark. Another remark. Remark 2. Let n be the dimension of M. Recall that J, which is gamma prime, and J equals T gamma prime are two Jacobi fields along gamma. These are the sort of uninteresting ones. The first never vanishes because gamma prime has constant length. We're looking only at non-constant geodesics, right? So this one never vanishes, and the second only vanishes at t equals 0. Right? This vector only vanishes at t equals to 0. I'll get your question in a second, Amanda. So hence, the multiplicity of a conjugate point is less than or equal to n minus 1. Okay, because we know that the geodesics, we want to have a geodesic which vanishes at time 0, and we know that the space of these, we're fixing the initial value, we're just not fixing the initial velocity. That's n dimensional, and we know there's already one in there which will never vanish after time 0. So that takes away one of them. So there's at most n minus 1 dimensional space of Jacobi fields which vanish at 0 and at some t naught. Okay, but in practice, it'll be less. In practice, it's less. The multiplicity will be less. Yes, question. Yeah. No, I didn't have to draw it like this. Besides, it's not just two-dimensional, right? It could be. Yeah, the space orthogonal to gamma prime is n minus 1 dimensional. On my picture, it looks yeah.
Comment.
Oh, the question. Sorry, the question was. It looks like this Jacobi field, which gives you a conjugate point, which determines a conjugate point, switches direction. But it's an artifact of the fact that my blackboard is two-dimensional. It's 0 at gamma of gamma 0 and 0 at gamma of t naught, and it actually could be 0 at other points as well, right? In this picture, I didn't exclude that from the definition. And we're just saying it's a non-zero Jacobi field. That means it's not identically 0, and it vanishes at gamma of 0 and at gamma of t naught. That's the only conditions. Okay.
Just comment.
Yeah.
I think on that board, J inverse should be J of t naught minus t. So wherever you have an A, put a t naught.
Yeah, that's better. I knew there was a problem. Yeah, so this is really, thank you. This is really, when I write gamma inverse, I take gamma restricted to 0 t naught, and I take the inverse of that curve. That's better. Okay. Okay, so let's do an example of conjugate points. Let's take Sn with the round metric. Okay, so as I told you when we talked about curvature, this has constant sectional curvature plus 1. This is the unit sphere, right? Radius 1. Okay, we didn't actually do that calculation. I told you you can do that calculation. And we know from the assignment that the geodesics are great circles. Okay, so let's draw a picture and investigate the conjugate points. I'm going to look at a geodesic, which is a meridian starting from the North Pole. So there's my picture of Sn. Let's look at a geodesic like this. It goes in the back after, and it closes up again. So this will be gamma of 0. So we saw when we talked about Jacobi fields, we proved that if you have constant sectional curvature and you only look for the Jacobi fields which vanish at the initial point, then we wrote down an explicit formula for the Jacobi fields. So the normal, and we only care about normal because in this first remark, we know that the ones that are not normal, that are tangential, will never give us conjugate points, right? Because they'll never vanish at a second point. The normal Jacobi fields, J, such that J of 0 equals 0, are given by J of t is sine of t, W of t, where W of t is parallel along gamma and orthogonal to gamma prime, right? We wrote down explicitly what the Jacobi equation is when you have constant sectional curvature, and we were able to solve it explicitly. And we had, there was values of k here. It was like sine something over root k, but k is 1. So if I draw a picture of that, let's use blue. So I'm taking, this is gamma prime of 0, the initial velocity. So I need a vector W, which is orthogonal, let's say a non-zero vector, which is orthogonal to gamma prime of 0. Then I can parallel transport this vector W all along this geodesic, W of t. I get a parallel vector field along this geodesic, and the Jacobi field, which vanishes, and a Jacobi field which vanishes at time 0 is given by multiplying this vector field by sine of t. So I need another color, green. So sine of 0 is 0. This is gamma of pi down here, right? Gamma of pi. Sine of t vanishes at 0 and pi. So this bad. And it starts decreasing again. You see this vector field will vanish only at time 0 and time pi. When it gets to time 2 pi, it's back to the same point again. So hence, gamma of pi, which is the antipodal point to gamma of 0, is a conjugate point, is conjugate to gamma of 0 along gamma. And the multiplicity, in this case, is exactly n minus 1, which is the most that it could be by that remark that we had a little earlier. And that's because there are exactly n minus 1 dimensional space of vectors orthogonal to gamma prime of 0. Right? This orange vector, there's n minus 1 dimensional space of choices for that. And then I can do this, and these will all be linearly independent. Okay, so this is not typical. As I said in the remark, we know that a given conjugate point can have multiplicity at most n minus 1, but in general, it won't be n minus 1. Okay. Let me make one more definition, and then we'll prove the last main result of this chapter. Okay, so definition, let P be a point in M. The set of first conjugate points, I'll explain this in a second, first conjugate points to P for all geodesics that start at P is called the conjugate locus of P. and it's denoted C of P. Okay, just some set, which could be empty. Could be empty. So you take the point P, you look at all geodesics that start from P, and you say, if I follow these geodesics, does there exist a conjugate point along there? In other words, is there some positive time after the initial time where there exists a non-zero Jacobi field along that geodesic that vanishes at the initial and that point? And when I say first conjugate points, remember the question that Amanda asked, I erased the picture now, that blue non-zero Jacobi field, I had it vanishing at gamma of 0 and at gamma of T naught. It could have vanished at some earlier point, right? And if that was true, then T naught, gamma of T naught would not be the first conjugate point along that geodesic, right? You look for the first point, the first positive time after T naught, after 0, where there exists a non-zero Jacobi field that vanishes at gamma of 0 and gamma of that time. And that's going to be the first conjugate point. So in the example that we did on the left-hand side with the sphere, so for the round sphere, C of P is equal to minus P. This is it consists of just one point. And again, this is not typical. So not only is it not necessary that every conjugate point has multiplicity n-1, it's also not true that the conjugate locus has to be 1 point. This is happening because the sphere has a lot of symmetry. Okay, so all the directions, all the geodesics coming out of 1 point, their first conjugate point is the antipodal point. It's the same for all of them. And we'll see examples today where there's no conjugate. Maybe not today. We'll see examples where the conjugate locus is empty. There's no conjugate points. Okay. So here's the theorem. I don't know if it deserves to be called a theorem. It's proposition in my notes, but I upgraded it. Let gamma be a geodesic. Let P be the initial point. Then the point Q, which is gamma of T naught, for T naught strictly bigger than 0 and less than or equal to A, is conjugate to P along gamma if and only if V naught, which is T naught times gamma prime 0, this is in TPM, is a critical point of XP. Okay, so i.e. XP star at T naught gamma prime of 0 is singular, not invertible. It has a non-trivial kernel. Okay, so in other words, the points where the exponential map fails to be a local diffeomorphism by the inverse function theorem are exactly conjugate points to geodesics emanating at P. So moreover, before we prove it, moreover, the multiplicity of Q as a conjugate point equals the dimension of the kernel of XP star T naught gamma prime 0. Okay. So these are the best kinds of proofs where they basically prove themselves from all the definitions. Let's just write out what we want to show. So Q is conjugate to P along gamma if and only if there exists a non-zero Jacobi field J along gamma with J of 0 equals 0 and J of T naught equals 0. Right? That's just the definition of conjugate point. Let's let V be gamma prime of T naught just to simplify things, and let W be J prime at time 0, the initial covariant derivative of this Jacobi field. So we proved earlier that J of T is XP star at TV applied to TW for all T in 0A. So what am I doing here? We had a formula that said if you had a Jacobi field whose initial value was 0, this is just for the Jacobi fields which vanish at time 0, and you know what J prime of 0 is, then you actually know what J is. We know that the initial value and initial derivative determine J, and it was given by this. When I wrote it down before the break, this V was gamma prime of 0, and this W was J prime of 0. That's the same formula. Okay, so we see that J is non-zero if and only if W is non-zero by uniqueness of the ODE theorem. Right? So if W was 0, if the initial velocity was also 0, we know the solution is 0, and you can see it here, right? And so if this is not 0, then the solution is not the 0 solution. So this J is not identically 0. Okay. So hence, Q is conjugate to P along gamma if and only if J of T naught is 0, and that's equal to XP star T naught V of T naught W for some W not equal to 0, which is equivalent to T naught V is a critical point of X. Right, because T naught is positive, so this gives us something non-zero in the kernel if and only if W is not 0. So that proves the first part. And the multiplicity of Q as a conjugate point equals the number of linearly independent Jacobi fields J that vanish at 0 and T naught. But J1 up to JK are linearly independent if and only if J1 prime at 0 up to JK prime at 0 are linearly independent, again by the ODE theorem. So these are all Jacobi fields that vanish at 0. Right? If they all vanish at 0, then their independence is measured by the independence of their initial covariant derivatives. And so the multiplicity of Q is equal to the dimension of the kernel of XP star at T naught V. Because what do we want to know? We want to know what's the space of solutions, the space of W's which satisfy this, right? That's exactly the initial, yeah, you can see from here, the kernel of this guy is exactly measuring the vanishing of J at T naught. Yep. It is because this is a linear ODE, right? And we said if there's a linear combination of these guys, which is 0, then if you take, let's say there's an A1 J1 prime of 0 up to AK K prime of 0 is 0. And if you look at the Jacobi field A1 J1 plus up to AK JK, that will vanish at 0, and its initial velocity will be 0 at 0. Therefore, by uniqueness of the ODE theorem, this will be 0 everywhere. It's the same thing, yeah, the same thing. Okay. All right, so that's the main, the final main result of the chapter on Jacobi fields, but we do have some bookkeeping to do it now. We're going to collect some very simple results about Jacobi fields properties, which are going to be used later in the term. So some more properties of Jacobi fields. And the first one I've already done 2 lectures ago when we defined Jacobi fields, but it's worth doing again, especially because the next 2 properties are immediate corollaries of this one. Okay, so first proposition, let J be a Jacobi field along a geodesic gamma. Then the inner product of J of t with gamma prime of t is equal to the inner product of J of 0 with gamma prime of 0 plus t times the inner product of J prime of 0 with gamma prime of 0. Okay, as I said, we already did this. I may have not phrased it exactly in this way. I think I did actually, but let's just do it again. So first of all, J gamma prime, if I look at this function, this is we know the Jacobi field is smooth and we know gamma, it's a geodesic, so the velocity is smooth. So this is a smooth function of t. If I covariantly differentiate this function along t, take d by dt of it, then that's going to be J prime gamma prime, because there's going to be another term which is J gamma double prime, but it's a geodesic, right? So gamma double prime is 0. And then if I do it again, I have to differentiate this with respect to time. And again, because gamma double prime is 0, I get this. And then by the Jacobi equation, this is going to be minus R J gamma prime, sorry, yeah, gamma prime, gamma prime. And this is 0 by the symmetries of the Riemann curvature tensor, right? I have the last 2 arguments are the same. So this function has second derivative equal to 0. So this function J of t gamma prime of t has to be some constant plus some constant times t. And you can see that C0 is J of 0 gamma prime of 0. And C1 is the first derivative of this function at time 0, which is J prime of 0 gamma prime of 0. Okay, so why did I redo this? Because we have 2 surprising corollaries of this, which are the following.
Could you ask the cameraman to move the frame?
Can we move the?
Like you're out of frame.
Okay, sorry about that. Okay, so the first corollary, if J inner product gamma prime at some time t1 is equal to J gamma prime at some time t2 for some t1 not equal to t2, in 0A, then J inner product gamma prime is independent of T. And in particular, if J at 0 and J at A are both 0, then J gamma prime is 0 for all T. So why is this? I'm not going to even write it down. It's immediate. Let's look at, okay, maybe I'll write it down. So proof, we have J gamma prime at T1 is equal to J gamma prime at T2. And this is equal to C naught plus C1 T1. And this is C naught plus C2 T2. But T1 is not equal to T2, right? The only way this can happen, sorry, is that C1 is 0. And that implies that J gamma prime of T is C naught is independent of T. And we know what C naught is. It's J naught gamma prime naught. So if the initial value, sorry, what did I write down here? That's right. So if J at time 0 and J at time A is 0, then certainly this is going to hold when I put T1 is 0 and T2 is A, right? Because J at T1 is going to be 0 and J at T2 is going to be 0. So this will hold. If this holds, then the hypothesis holds. And therefore, this holds for all T, but this is 0. Okay, so what we've seen is that if we have a Jacobi field which vanishes at the two endpoints of the geodesic, then it's orthogonal to the velocity for all time. Let me write it over here. So if J of 0 equals J of A equals 0, then J T inner product gamma prime T is 0 for all T. Okay. And another corollary of this proposition, corollary 2, suppose J of 0 equals 0, then J prime 0, gamma prime 0 is 0 if and only if J prime of T, gamma prime of T is 0 for all T. Certainly, if J prime of T is orthogonal to gamma prime of T for all T, then this will hold at time 0. But we're saying that as long as it holds at time 0, it's going to hold everywhere. And it follows from here, right? Because if it holds at time 0, then this second term in the expression, what did I write down? Sorry, this is, sorry. This should be a J, right? If the initial, so we're looking only at Jacobi fields which vanish at time 0. If the initial velocity was orthogonal, if the initial covariant derivative of J was orthogonal to the initial velocity of the geodesic, then the Jacobi field is orthogonal to the velocity of the geodesic everywhere. Okay, and it follows from here because if J prime of 0 dot gamma prime of 0 is 0, this term goes away, and J of 0 is 0. So this is immediate. But the punchline of this guy is that if we only care about the normal Jacobi fields, the one, this is repeating what I said earlier, the Jacobi fields which are everywhere orthogonal to gamma prime are exactly the ones, sorry, the Jacobi fields with initial value 0, which are everywhere orthogonal to gamma prime, are exactly those whose initial covariant derivative is also orthogonal to the initial gamma prime. Okay. All right, one more result. Well, one more proposition and one more corollary, and we're done with Jacobi fields for the time being. So let gamma be a geodesic. Let V1 be a tangent vector at the initial point of the geodesic, and V2 be a tangent vector at the final point of the geodesic. Okay. Then if gamma of A is not conjugate to gamma of 0 along gamma, then there exists a unique Jacobi field J along gamma with J of 0 is V1 and J of A is V2. So if you go back to your background on ODEs, right? The ODE theorem says that if you give initial conditions, there's always a solution, right? The initial value of J and the initial derivative of J, then there's going to be a unique solution. Here, we're asking the boundary value problem, right? We're saying if we want to specify not the value, the initial value and the initial derivative, but the initial value and the value at some other point, can we find a Jacobi field which has this value V1 at time 0 and this value V2 at time A? And we're saying that if gamma of A is not conjugate to gamma of 0, then there exists a unique one with this property. So let's see how that works. So let script J be the space of Jacobi fields along gamma with initial value 0. I guess I want, yeah. So this is an n-dimensional vector space. I'm not excluding the tangential one. Okay, and let's define a map capital F from this space to the tangent space at gamma of A of M by F of J is just evaluation at A, evaluation map. Okay, so this is a linear map between n-dimensional vector spaces, right? If I evaluate J1 plus J2 at A, I get J1 at A plus J2 at A. Similarly, for a multiple. So since gamma of A is not conjugate to gamma of 0 along gamma, F is injective, hence an isomorphism. Right? What does that mean? So this is a linear map between two n-dimensional vector spaces. So to know it's injective, I need to know the kernel is 0. Well, suppose I have something in the kernel, that means J of A vanishes, right? J of 0 vanishes and J of A vanishes. So if there was some non-zero J which does this, then gamma of A would be conjugate to gamma of 0. But my hypothesis is gamma of A is not conjugate to gamma of 0. So the only J's that are in the kernel is the 0 J. So it's injective, hence an isomorphism. So there exists some J1 hat in J such that J1 hat of A is V1. Right? Because it's an isomorphism, that means it's onto. So V1 is in V2, sorry, V2. And now we do the same thing in the opposite direction. So gamma of 0 is not conjugate to gamma of A along gamma inverse. Because if it was, then gamma of A would be conjugate to gamma of 0 along gamma inverse. So by the same argument, there exists a Jacobi field along gamma with J at A is 0. Let's call it Jacobi field J2 hat along gamma with J2 hat at A is 0 and J2 hat at 0 is V1. So this guy has J1 hat at 0 is 0. Okay, so then J, which is J1 hat plus J2 hat, is a Jacobi field along gamma with J at 0 is V1 and J at A is V2. And the uniqueness is clear, right? Because if there was two of these, then their difference would be a Jacobi field which vanished at the two endpoints, but that would mean the points were conjugate, but they're not. Uniqueness is clear. And I'll just say it again. You suppose you have two such J's, look at their difference. It's a Jacobi field along gamma, it vanishes at 0 and at A. Because those points are not conjugate, the difference has to be 0. Okay. Last corollary of the section. Let gamma be a geodesic. Let script J perp be the space of Jacobi fields along gamma with J of 0 equals 0 and J prime of 0 orthogonal to gamma prime 0. So in particular, by corollary 2, J of t is orthogonal to gamma prime of t for all t. So this is still the hypothesis. So we're looking at those Jacobi fields which are everywhere, which have initial value 0 and which are normal Jacobi fields. Let J1 up to Jn minus 1 be a basis of J perp, because we know that this is n minus 1 dimensional. Then if gamma of t is not conjugate to gamma of 0 for all t in 0 up to A, then J1 of t up to Jn minus 1 of t is a basis for the orthogonal complement of gamma prime of t in TPM, T gamma T of m. Okay, so this guy is in here. All the Jacobi fields, all these guys, their values at time t are orthogonal to gamma prime of t. So at time t, these are certainly vectors in here. We're saying if they're a basis for this space, then at every time t, they're basis for the orthogonal complement of the velocity of the geodesic in the tangent space at that point. And this proof is exactly like the previous one. Let's define f from J perp to T gamma T of m, which is f of J is just evaluate at time t. This is linear. maps into the orthogonal complement of gamma prime of t, because the value at time t is always orthogonal to gamma prime of t. So this is mapping from this n-1 dimensional space into the n-1 dimensional subspace of t gamma of t, which is orthogonal to that guy, and f is an isomorphism if and only if f is not if and only if f is injective, because the dimensions are the same, and that's if and only if gamma t is not conjugate to gamma 0. The same argument as before. Okay. So that was a bunch of sort of simple propositions and corollaries about Jacobi fields. As I said, we're going to be using these things in the coming weeks, and I'll remind you, this is something we proved at the end of chapter 5. So are there any questions about that before we completely switch gears? All right. So what comes next in Do Carmo, we could have done several weeks ago. It's kind of strange how he chooses to order the topics, but we're going to follow basically his order. The next thing to do is to show that if you have a Riemannian metric on a manifold, you obtain a metric in the space of metric spaces. So every Riemannian manifold, as a set, together with a distance function, which I'm going to define now, becomes a metric space, at least a connected Riemannian manifold. And then you can ask, well, if you have a metric space, you get a topology. How does that differ from the topology that M has as a manifold? And we'll see that it doesn't differ, it's the same. And then you can ask, well, what nice properties do metric spaces have? A metric space, the best kind of metric space is a complete metric space. Okay, and what does that mean in terms of the Riemannian metric? For the metric space to be complete, it's going to be equivalent to what's called geodesically complete, which is equivalent to all the geodesics exist for all time. Okay, so this is not obvious, but it won't be hard to prove. So that's the Hopf-Rhino theorem and various characterizations of completeness. So we'll start that now. We'll probably finish it sometime on Wednesday. And then we're going to get to what's called the Cartan-Hadamard theorem, which is our first sort of global result, right? Where we assume some local information about the metric and we deduce a global topological consequence. Okay, so this part is completeness. And the Hopf-Rhino theorem. I don't know how to pronounce rhino. I'm assuming that's how they do it, but it's probably wrong. So let's start with a definition. I think I gave this definition earlier, but I'll do it again. So let Mg be Riemannian. We say the metric G is geodesically complete if and only if, for all P and M, XP is defined on all of TPM. Okay, so equivalently, for all P and M and for all V in TPM, the geodesic gamma V with gamma 0 is P and gamma V prime at 0 is V is defined on all of R. Remember, we know that given an initial point and an initial velocity, the geodesic will be defined on some open interval containing the origin. And we can take the maximal open interval on which it's defined, but we've already seen examples that this doesn't have to be all of R. So if it's true that every geodesic with every initial point and every initial velocity is defined for all of R, we call that Riemannian metric geodesically complete. So of course, on the same manifold, you can have different Riemannian metrics, and some of them might be geodesically complete, and some of them might not be geodesically complete. Okay, so that's the definition. So from now on, unless I say otherwise, let's suppose M is connected. If it's not, we just do this on every connected component. They don't see each other, they can't communicate. So then MG becomes a metric space as follows. So I have to define a distance function and prove that it's a distance function. Okay, so let's let P and Q be an M. There exists a piecewise smooth curve joining P to Q. So here I'm using the fact that it's connected. So in fact, you can do this with a smooth curve, right? Because if it's piecewise smooth, it has a finite number of possible sharp turns in its velocity vector. You can just sort of zoom in there with a coordinate chart and you can smooth it out easily. But I'm going to prefer to use piecewise smooth curves because I want to get the triangle inequality for a metric space. Okay, so I really care about the set of piecewise smooth curves joining P to Q. And this uses the fact that M is connected. Uses M is connected. Okay, so let's define the distance from P to Q. This is going to be the distance from P to Q. It's going to be the infimum over all piecewise smooth curves alpha joining P to Q of the length of alpha. Okay, we know there's at least one curve from P to Q. It has some length, which is non-negative. It might be 0 if P equals Q. And then so there's a whole set, a non-empty set of such curves. And these are all non-negative real numbers. I'm taking the inf of a non-empty set of non-negative real numbers. So this is a non-negative real number. Okay. So what we want to do is show that this makes M into a metric space. The lemma MD is a metric space. Okay, so it's clear. So we already know that D of PQ is greater than or equal to 0. And it's clear that D of PQ equals D of QP. It's symmetric, because anytime we have a curve from P to Q, we can follow the inverse curve and get a curve from Q to P, and those have the same length. Okay. Let's look at, so remains to show the triangle inequality and that dpq equals 0 if and only if P equals Q. Okay, so we have to prove those two things. So let's let P, Q, and R be points in M. So I know that there exists some curve alpha 1 from P to Q, piecewise smooth curve. And there exists some curve alpha 2 from Q to R. So if I follow first alpha 1 and then alpha 2, and this is why I want to use piecewise smooth curves, I get a piecewise smooth curve from P to R. So alpha 1 followed by alpha 2 is a piecewise smooth curve from P to R. Okay, and it has a length equal to the length of alpha 1 plus the length of alpha 2. That's how we define lengths of piecewise smooth curves, by adding up the lengths of the pieces. So the distance from P to R is certainly less than or equal to the length of this curve, because this is a piecewise smooth curve from P to R, and that's equal to L of alpha 1 plus L of alpha 2. Now let's take the inf over all alpha 1s from P to Q, and then the inf over all alpha 2s from Q to R. Take inf over all alpha 1 from P to Q. We get that the distance from P to R is less than or equal to the distance from P to Q plus L of alpha 2. And now take the inf over all alpha 2 from Q to R. And we get that the distance from P to R is less than or equal to the distance from P to Q plus the distance from Q to R. So that's the triangle inequality. One more thing to prove. So it's also clear, and I'll say in words, that d of p equals 0. If you like having the constant curve as being one of your piecewise smooth curves, then there's no problem there, because the constant curve is a piecewise smooth curve from P to P and it has length 0. If you don't like that, just take an open neighborhood of P, let's say a coordinate neighborhood, and just look at little loops going from P to P, and you can make those as small as you want, right? So the inf is 0. Okay? So it remains to show that the distance from P to Q equals 0 implies P equals Q. And this is the only non-trivial part of the argument, and this is where we're going to use some Riemannian geometry. So suppose that the distance from P to Q was 0, but P is not equal to Q. We need to get a contradiction. Let B epsilon of P be a normal ball centered at P, that does not contain Q. Right? We can do this because since P is not equal to Q, the manifold is Hausdorff. I can find an open neighborhood of P which doesn't contain Q. And within that open neighborhood, I can shrink it to get a normal ball centered at P that does not contain Q. Let's draw a picture. This is P, and this is B epsilon of P, and Q is somewhere outside. So epsilon is some positive number. Since dpq is 0, is less than epsilon, there exists a piecewise smooth curve alpha joining P to Q with length less than epsilon. Right? Because the distance is the inf over all such lengths. And since the inf is 0, for any positive number, I can find a curve whose length is less than that. But the segment of alpha contained in B epsilon P has length at least epsilon by the locally length minimizing property of geodesics. Well, by, let's say, properties of normal balls, right? Properties of normal balls. I'll draw a picture and I'll explain it. And that's our contradiction, so P equals Q. So what do I mean here? We proved that if you're in a normal ball, and remember, for a normal ball, that means that the closure is also contained inside the image of a point of a of an open set on which the exponential map is a diffeomorphism. So this part of alpha is the part before until it first hits the boundary of b epsilon p. That's a curve from p to some point r on the boundary. But we know that this curve is the unique minimizing geodesic from p to r, because this is a normal ball. And this curve has length epsilon, the radius of the ball. So this green curve, which is the part of alpha until it first hits the boundary, already has length length at least epsilon, because this one is the shortest one. And therefore alpha has length at least epsilon. But there's our contradiction. Okay, so we use the fact that we know we can find a sufficiently small neighborhood of P, which is called a normal ball, where we know the distances, that we know the lengths of the shortest curves between 2 points there. The unique minimizing geodesic. Okay, so this gives us a metric space. Now we can ask all the nice questions about metric spaces. So let's make a note. If there exists a minimizing geodesic gamma joining P to Q, then the distance from P to Q is the length of this minimizing geodesic. But such a gamma need not exist. We haven't proven that any 2 points can be joined by a minimizing geodesic. By the way, is a little bit of redundancy here, right? Because we proved a few weeks ago that if you had a minimizing curve joining 2 points, in other words, it's a piecewise smooth curve joining those 2 points, and its length is less than or equal to any other length of a piecewise smooth curve joining those 2 points, then it had to be a geodesic, right? So you can't have a minimizing curve that's not a geodesic. But of course, not every geodesic is a minimizing curve. And we also know that a geodesic is smooth, so it won't be piecewise smooth, it'll actually be smooth. So whenever we can join 2 points by a minimizing geodesic, then it's easy to compute this if it's just the length of that geodesic. Hence, if epsilon positive is sufficiently small so that b epsilon of p is a normal ball centered at P, then b epsilon of P is exactly the set of all points in M such that the distance is less than epsilon. Okay, so the notation is consistent with what you're used to using in metric space notation, right? You would like this to mean the set of all points in your metric space whose distance to P is less than epsilon. Okay, we already defined what this guy is a few weeks ago, and we only made sense of this for epsilon sufficiently small. Metric balls you can define for any positive radius. Okay, but what we're saying is that if the radius is small enough, then a metric ball is exactly a normal ball. And that's because we're in this setting, right? If you take any points, if you take any point outside of here, then the distance is bigger than epsilon to that point. Because again, this argument, you're going to hit the ball at some point, and that already has distance at least epsilon. So if you're outside of here, you're outside of here. And if you're in here, because it's a normal ball, we know that the distance is exactly the length of the radial geodesics. Okay? So what this says, so hence, if epsilon is sufficiently small, a normal ball, b epsilon p, is a metric ball. And by metric ball, I mean this right-hand side. Okay. So the corollary to this, and I think that's probably a good place to stop, is that the topology induced by this metric space metric is the same as the original topology. So let's see why that's true. Corollary, the topology induced on M by the metric space metric or the distance function D coincides with the original manifold topology. And I claim that's immediate from that remark, but let's put in the details. Okay, so what do we need to show that this coincides? We need to show that if you have an open set in one, it's open in the other and vice versa. Okay, so proof. Here's let U be open in the metric space MD. Okay, so then there exists, let P be in U. There exists some epsilon positive, which I can take sufficiently small such that the metric ball, so this means the ball of radius epsilon with respect to the distance function, is equal to the normal ball and is contained in U. Okay, so I know because it's open and this is a metric space, I know there's some metric ball centered at P contained in U. And so I can take the radius of that metric ball smaller to make it the radius of a normal ball, and then it's contained in U, and hence, and this is open in M. The ball of the normal ball is open in M. And therefore, what I can do, so here's the picture. B epsilon P, which is B epsilon D of P, is open in M. So for every point P, I can find an open set in M, which contains P and which is contained in U. That means I can write U as a union of these guys, and they're all open in M. So U is open in M. And conversely, suppose V is open in M, and let P be in V. There exists some epsilon positive, again, sufficiently small, such that B epsilon P, which is the same as B epsilon D P, is contained in V. And this one is open in the metric space. Okay, again, how do I know this? Because V is open in M, P is in V, so I can find an open neighborhood. I can shrink V. I can find a small enough open neighborhood of P in V, which is a normal ball, and then it's a metric ball. So again, by taking the union over all of these, so V is open in MD. Okay. And then the last thing to say, corollary. So by the way, you see that the original manifold topology was there before we put a metric on it, right? And there's lots of different metrics you can put on there. But what we're saying is that all these metrics, all these Riemannian metrics, they all give you different metric space metrics, different distance functions, but the topology that these distance functions gives you is always the same. It's the one from before. Completeness is not a topological property, it's a metric space property, right? So you can have two different distance functions coming from two different Riemannian metrics on M. They're going to give you the same topology, but one might be complete, one might not be, because that has to do with the metric distance. So final corollary, let P naught be a point in M. The function F from M to R given by f of q is the distance from P naught to Q is continuous on M. And that's basic metric space theory. Right, the distance function of a metric space is always continuous. Okay, so this function, distance to a fixed point, is a continuous function. We're going to stop here. So next time, we're going to, now that we know that our manifold is a metric space, we can ask, is it complete as a metric space? And we'll see the punchline. I'm spoiling it for you, but you should still show up on Wednesday. The punchline is the Hopf-Rhino theorem, which says that as a metric space, it's complete if and only if that Riemannian metric is geodesically complete. Okay, which is not at all obvious, but it won't be that hard to prove. And after that, we're going to prove the Cartan-Hadamard theorem. So I'm going to need to tell you some facts, which you may or may not know, about covering spaces and fundamental groups and deck transformations and all that stuff. So I'll probably prepare a handout and give it to you as sort of supplementary, because there's a minimum amount of topology that from now on would be helpful, but I'm not assuming you all have it, so I'll just tell you what it is. Okay.